Good morning from London and welcome back to the Fastly YouTube channel for the 9th in our series of developer live streams, where I'm joined today by Andrew Betts, who you may remember from a previous episode.
Hi.
Today we're going to be learning about how a modern content delivery network can keep your site running smoothly and your customers happy during busy periods such as the holiday shopping season. So what are we going to be showing off today?
Well, when we talk about dealing with very high traffic events, then the main weapon at our disposal is caching. So we're going to be talking a lot about getting the cache hit ratio of your site to be as high as possible, to be able to serve as much as possible from cache. And that involves techniques like purging, understanding how to purge things once they're in cache, request collapsing, shielding, and things like request normalization.
So some of these are common behaviors of CDNs, but some of them are also unique to Fastly. So we're going to explore all of them in depth and see how this can help your site run smoothly. So should we start off by talking about caching?
Yep, absolutely. So if we can look at my screen, first thing we see is here is the developer hub, developer.fastly.com. And right on the homepage, there's a few things here which are worth kind of talking about in the context of scale and caching and why edge networks are important. So we have thousands of servers, over 5,000 servers all around the world in 98 POPs as of today. And that gives us the ability to handle a really vast amount of traffic. And that's important because, if you may currently have nowhere near that amount of capacity, and you may not need that amount of capacity, but if you suddenly do need a large amount of capacity very quickly, then having an edge network like Fastly in front of your website is a very good way to be prepared for that kind of scenario. So right here on the homepage, you can see the number of requests per second that Fastly is handling, which is currently around 30 million requests per second. We are pushing about 50 terabits a second across the network. And those are giant numbers. Before I joined Fastly, I had no concept of being able to handle 30 million transactions per second in any kind of system. So it's incredible to me that we do that. The other thing that's worth looking at here is the cache hit ratio, 91% right now. That's pretty typical, and that means that for every 10 requests we receive on behalf of end users, we only need to send about one of those to a customer's systems. And so as the higher we can get that, the more leverage effectively you have to handle more traffic with the same amount of infrastructure. The other thing a couple of things I really like about this page. One is that we added this thing that shows you which Fastly POP served this page to you. Which is a really nice way of making the idea of an edge network a little bit more practical. We're often drawn on architecture diagrams as a big cloud. And the reality is, we are actually in physical buildings in various cities around the world. Just enter developer.fastly.com in your browser and you'll find out where your nearest Fastly POP is. If I scroll down here, you'll also see we have a neat little visualization here that shows you some traffic happening in real time for 3 of our fast forward partners. So these are organizations that we support with free service because they, do good things for the internet. And this gives you a really nice visual understanding of the effect of having an edge network, which is to say that traffic starts to happen very much more locally than if you just are serving everything from one location. You effectively can serve all your users in their region, hopefully even in their city, in many cases. So let's talk about how we can start to do that by making sure as much of your site is cached as possible. So diving into some more detail on the developer hub, this is the cache. I'm going to go to cache interfaces page actually. So I'm in the learn section here in core concepts, edge state and caching, and then cache interfaces. And this gives you a summary of the cache features that Fastly provides. So most Fastly servers are basically giant buckets of storage, and across the whole network we have a vast amount of storage capacity which we expose to you as a number of different cache interfaces. And if you don't know which one of those you're using one called the read-through cache, which is a cache that automatically stores things that pass through Fastly on their way from your servers to your end users. And whether or not we store that content depends on a couple of things. One is the HTTP status, and one is the response headers like cache control, surrogate control, and expires. So we're going to be talking about specifically the read-through cache for the rest of today, and I'm going to mention first of all these HTTP semantics, because these are really important. So if I go into the cache freshness and TTLs page here, you can actually see that we document here these conditions that I'm talking about. And I think one of the most important things especially for sites that are looking to guard against very high traffic events and prepare for high traffic events, is to think about these statuses and the default handling of these kinds of responses by the cache. Because by default, Fastly will cache certain status codes, 200, 404, these are examples that we cache, and any others we won't. So for example, a 500 internal server error, or a 503 or a 403 forbidden, we don't cache those by default. So if your servers were suddenly to start behaving differently, or you were to start receiving a different pattern of traffic that elicited different kinds of responses from your servers, then you might find that the proportion of traffic that we can handle from cache changes quite dramatically. And of course you can reconfigure this, you can change which statuses we cache and which ones we don't, but understanding which statuses are going to cache is quite important. And then once we've decided to cache something, the headers like surrogate control, cache control, and expires are important to deciding how long we're going to cache that content for. Now let's have a look at a little example. So I have here Fastly Fiddle, which is a tool Kayla and I mostly wrote over the last few years. And it allows you to play with Fastly by creating kind of ephemeral Fastly services. You can write edge code, you can set up your own origin servers, you can configure requests, and then you can see what happens when you run those requests through Fastly servers. So I'm going to set this up with no code, so completely default configuration. I'm going to use a Glitch app as the backend. Now Glitch is another playground platform where you can create static websites with Node app. It's actually quite fast now. We'll talk a bit more about Glitch later, but for now, just think of this as a really, really simple little Node.js application that is giving me back a predictable response that I expect. So I'm going to ask my backend to respond with a 200 OK status and give me a response that I can cache for 1, 2, 3, 4 seconds. And then I'll make exactly the same request again. So let's run that and see what happens. Okay, so we made a request to Fastly. It had these headers. Then these orange blocks represent states within our VCL state machine that tells you how we've processed that request and how it's kind of forked through the state machine. Then we made a request to the origin server. The origin server responded. We decided we can cache this for 21 minutes, which is 1, 2, 3, 4 seconds. And then we sent the response to the client. Then the second request came in for exactly the same URL. And this time, as you can see, it was a hit. Now, I was very confident that that was going to happen because Fastly is very eager in our policy on caching. So we only need to see something once that's cacheable, and we will cache it. And the way that our servers will cluster requests to designated storage servers means that you will very likely get a hit if you try and request the same thing again from the same location. Now we could have a different policy. We could have a policy where, say, we need to see things a few times before we cache it, but and that would probably mean we'd write to cache less and we would maybe hold on to things for longer. But I think this is a better way to do it because it means that we get a better developer experience as well. You will know if you didn't get it right, if you didn't set your cache settings correctly, because if we didn't cache it, it's because you told us not to. So let's have a look. This is one single request that we're looking at here in isolation. Let's look at what happens when we have lots of requests coming in and we want to see some more like aggregated metrics of what's going on. So here, this is a back-end view of the Fastly control panel for Kubernetes, who are another one of our fast forward partners. Very kindly allow us to show their Edge Observer statistics publicly, so we can kind of use them as a demonstrator. So this is a product we call Edge Observer, and it shows you a lot of useful information about the traffic that is going through your service. And there's a couple of things I'll draw attention to here. One is that we're showing the live cache hit ratio, which is hitting 100% fairly regularly on a 1 second sample, but is dipping down when they receive requests for things that are not the current latest binary of Kubernetes. And then the other graph, which is really interesting to me in relation to what we're talking about today, is the cache coverage. Now this graph shows you the proportion of all the URLs on your site that are in our cache. And this is expected to be significantly lower than your cache hit ratio because, of course, you're receiving most requests for a small number of URLs. And there will be potentially, some websites have an infinite number of URLs, and many of those will never receive a single request. But you will probably have a lot of content on your site that is very rarely requested, and so that will fall out of cache regularly. But understanding approximately what is your cache coverage, how is it changing over time, how does it change as your traffic increases or as your patterns of traffic change, helps you to understand what the behavior will be when you hit a peak load. So that's looking at an aggregation of a lot of traffic from Fastly's perspective. Let's also look at how a complete site loads from the front end and debug that from a caching perspective. So this is the Financial Times, ft.com, which is a Fastly customer. And if I open the Chrome DevTools, go to the Network tab, and then reload this page, we can see flashing past there all of the requests that are being made to render this page. Now, to understand how many of these responses came from cache, I can look at an individual response, and I can see the cache control header here that's being emitted by Fastly. And I can also see that there's a header which is, it's not proprietary to Fastly, but it's a non-standard HTTP response header called xcache, which in this case is showing a miss. So it's showing that this page was not found in the Fastly Edge cache. If I refresh this page, I imagine I will probably get a hit. Let's have a look. Yes, so second time around, I did get a hit. Now that's if I want to look at one individually. Now what if I want to see that information across all of the requests that made up the loading of this page? There were 165 requests here. So if I right click on the header area of the DevTools network table, I can go to response headers and actually add the cache control header to the table. So now I can see the cache control value for every request that was made in the loading of this page. And this is one I really like. You can go to response headers, manage header columns, and I can actually add that xcache header as well. So now I can see not just what the cache policy on every individual response is, but I can also see whether each response that made up this particular load of the page was a hit or a miss in the edge cache. And in fact, we can see that the FT does extremely well. Like most of the resources they're loading from their own domains are hits. There are a few here which are coming up as miss, hit, interestingly, and we will come on to why that is in a minute. But that's like an initial overview of how we think about caching at Fastly, how we get things to be cached, and how we can start to think about debugging that.
Well, to summarize that, I'd say that Fastly caches by default. The automatic cache, as Andrew said, is called the read-through cache, and it caches certain HTTP statuses by default. That would be 200s or 404s. It doesn't cache some of them, like 403s and 500s, as you don't want to cache an error from the server when that is likely to change on a different request. But you can change this behavior using VCL if you would like. We obey HTTP cache header directives like cache control, which are standard. And we show the amount of content that's being cached using a metric called cache hit ratio, which is the proportion of end user requests to origin requests. So if you had one origin request for every 10 end user requests, that would be a cache hit ratio of 90%. The amount of your site that is cached is likely a lot lower than that, but we can improve that. We'll show you how. And the way that you can understand how much of your site is being cached is by checking the response headers, or using Edge Observer, which is the dashboard that Andrew showed. And you can actually do both of these things. We would recommend that you keep an eye on all of them in order to optimize the cache efficiency of your website.
And now let's look at what you might want to set those cache control header values to, because one of the most common questions we get is, what should the correct value of cache control be? So there are a lot of different values that we see. A lot of them are not very well thought through. A lot of them are maybe even contradictory. But actually, there's really only three, in my mind, types of content, or like big categories of content from a caching perspective. And these are they. So first of all, the content that we like the most is immutable content. So this is stuff that you publish at a URL and it then never changes. So it might disappear at some point in the future, but it will never change into something else. And this is often the case with things like JavaScript, CSS, images, where you've got some kind of build system that inserts a fingerprint or a hash or a signature, whatever you want to call it, into the URL. So whenever you change even a single byte of that content, it will get a new URL. Sometimes this is done using version numbers instead of checksums, but basically the same principle. Basically, you change the file, you change the URL. And so that means the file is immutable. So the best cache control value for that kind of content would be public, because it is public content. We can share that content to multiple users with a very long max age. Think in terms of years. Like 1 year is probably fine, because in practice, like if you give anything a max age of a year, it's unlikely to stay in the cache for quite that long. It is effectively forever in internet terms, and throw in the keyword immutable. Now the immutable keyword doesn't make a huge difference to Fastly, but it means that from the browser's perspective, if you serve a resource with immutable in the cache control header, then if the user refreshes the page, the browser actually won't refresh that resource because it knows that it can never change. So if it has a copy of it, there is no point in fetching it again. So that's what we should do with immutable content. Second category of content, personalized content. So this is any content that has, any resource that has content that is specific to a single individual and is, usually private to that person. So think in terms of shopping baskets, inboxes, account detail screens, anything really that is part of a web app that contains private or personal data. So these kinds of resources should have private directive to tell shared caches like Fastly that we absolutely must not copy this resource to any other user. It's really important that you include the private directive there and not just no store or no cache, and also no store, because you also want both the browser and any shared caches to not store this resource in cache. And then the third general category of content is stuff that is public but might change. So in this case, we want to include the public directive. We want to give it a very long S max age because we want it to be stored in a cache that we control, i.e. Fastly, for a long time until it changes. But in caches that we don't control, like browsers, we will want it to have a very short max age or possibly not actually cache in the browser at all. And this was the case for the FT, for example, the example we just showed you. Their homepage is no cache in the browser, but does have a long cache duration at the edge. And this is also a scenario where it can be really helpful to make use of stale cache behaviors, which we'll get onto in a minute. So this is the sort of content where you're going to want to use a stale or a validate and a stale if error directive. So think about all the content on your site in terms of which of these three buckets though the content falls into, and you should end up with a pretty sensible caching policy.
Fantastic.
What's
So
next?
you mentioned that you had set like a long max age on content that's public. If it's going to be a really long max age, obviously it's going to be cached even if you have changed it. Is there a way that we can kind of purge it from the cache?
Exactly, purging. So in that last scenario, this is the one where purging is really important. Obviously, it's possible that you're going to want to fix problems with your configuration or whatever that will require purging the cache. But in a normal operation, the kind of content that benefits from being able to be purged is content where it might change, but it doesn't change on a predictable schedule. So that's that last bucket of content. Content that's public, that we're telling the browser not to cache, but we're telling Fastly it can cache for a long period of time. So let's think about how we can make use of purging to make Fastly's caching of that content particularly efficient. And we do this by setting a very long S max age, so Fastly can store it for a long time. And then when it changes, you would use purging to tell Fastly to delete it. Now, purging can be done in a number of different ways. This is the documentation for our purge system, and we support a number of different types of purge. So the three main ones are a single URL purge, a surrogate key purge, and a full purge all. Now, purge all is a very convenient thing to do, but is generally speaking a very bad idea if you have a site that's under load, because if you are experiencing high amount of traffic, then purging everything in your cache is going to result in all requests going to your own infrastructure. So do think carefully before you issue a full service purge. Equally, like doing single URL purges can be quite difficult because you may have a lot of stuff that you need to purge. And it's kind of inflexible. The best kind of purge is a surrogate key purge. It's very fast. We execute them in 1 to 200 milliseconds, and it allows you to purge any distinctly identifiable set of content. So if I just go down here to adding surrogate keys, we can see how we can add effectively tags to our content by including a surrogate key response header. And that you can add any number of tags to a piece of content, and a tag can be associated with any number of pieces of content. So, for example, if you have a particular product, you could have a tag which is like product and then a number, and you could put that tag on any page that contains a mention of that product, whether it be the actual product details page, or whether it be a category index page, or even a search result page that mentions that product somewhere. And then when you issue a purge for that key, you are going to purge all resources that mention that product and nothing else. And that means that you're going to create the most efficient use of the cache, because we can still use everything else that's in the cache. We're just getting rid of the minimum amount of stuff that we need to because of that content change. Let's look at that in a fiddle. So here I have, again, a same tool that we were using earlier on, and I'm using the same origin server, and I'm asking it to give me a 200 OK response with a header that says surrogate key product 4. And I'm also including a cache control header that has a very long S max age and a shorter max age, which is basically what we were recommending earlier on in terms of best practice for public content that might change. So here we are seeing a miss and a fetch from the backend, which is then stored in the cache and returned to the user. Let me run it again. Second time around, I get a hit as I expected, and I can now run this as many times as I like, and I'm just going to keep getting hits. But I can use the purge a key feature within Fiddle to purge a particular surrogate key. I'm going to purge product 4, which I think is the right tag. And now if I run it again, this time, as expected, I get a miss because I have purged all content that is tagged with that surrogate key, and this particular URL was tagged with that key. So this is a really efficient way of creating targeted purges that then enables you to set very long TTLs for all the content in your on your site.
Great. Well, to summarize purging, purging allows for eager caching. Because you can purge resources on Fastly, you can set a long max age and store it for a long time. To clarify, that's a long server max age. You, of course, cannot purge things that are in people's browsers, so the S max age indicates the time that it will be cached at the edge. You can purge single URLs, or you can purge by tag, which is the surrogate key feature that Andrew was talking about. And this takes around 150 milliseconds to clear the tagged items from the global cache. There's also soft purging, which marks things as stale instead of immediately removing them from the cache. And this allows things to be revalidated in the background with a feature that Andrew is going to mention shortly, which is stale requests.
Okay. Yeah, I didn't mention soft purging, and I should have done. So most purges are intended to, you think of them as deleting stuff from the cache, and that's fair enough, right? Like you think purging actually sounds like a fairly aggressive thing to do. So you think of it as deleting everything from the cache, and if you want to make sure that we don't serve that content ever again, then that is what we call a hard purge. But we do also have an alternative form of purging called a soft purge, and it's just a flag that you can supply when you make your purge request. When you do that, instead of considering that object to be completely evicted from the cache, we will consider it to be stale. So let's talk about what staleness means. Staleness is a state that content can be in when it has reached the end of its TTL, its time to live, but it is still within a period that has been designated when it can be used under certain circumstances, and certain kind of narrowly defined circumstances. And there are two of those. One of them is called a revalidation period, and one of them is the stale of error period. So you can see here in illustration, this is the staleness and validation docs. All of these documents I'm showing you, by the way, are all within the edge state and caching section of our Learning Center on the Developer Hub. So if I include stale or validate and stale of error in the cache control response cache control response header for a resource, then I'm going to set up a policy that looks a bit like this. For the first 5 minutes, this resource will be considered fresh. So if Fastly receives a second request for it, we will just dig that resource out of the cache, throw it back to the user, and call it done. We won't need to interact with your origin server at all. For the next minute, so that's stale validate equals 60, we will take that object out of the cache and serve it immediately back to the user that requested it, so they get a nice fast response. But we will also, in parallel, make a request to your origin server to get the updated version of that content. And when we receive that content, it will replace the existing item in the cache. This is a really cool mechanism because it means that if you use it properly and you have enough regular traffic to a particular resource, then it will be regularly updated, but no user will ever encounter a blocking request to origin. And then finally, we have the stale of error period. So if we've exceeded that additional 60 seconds, we're now in this 1 day long stale of error period. If we receive a request during this period, we will make a request to origin. We won't use the object that's in the cache. We will have that user wait, make a request to the origin server, and only if the origin server is down or fails to give us a valid response will we then dig that item out of the cache and use it. So it's very much a policy where we say use this only if you really, really need to. Now, we have a little demo here of this behavior as well. So let me rerun this. So what I'm doing here, again, exactly the same origin, no configuration, exactly the default Fastly behavior. I'm asking my origin server to give me a 200 response with a cache control header that says stale or validate 60, max age 10. Now, what this means is that for the first request, which I'm actually just going to run again, first request, I will see a miss. because we're fetching that for the first time. If I run it again within 10 seconds, then I will get a hit because the object is fresh in the cache. We're within that max age 10, that first fresh period. Now if I run it again outside of that 10 seconds, but inside of the 60 seconds stale while revalidate period, we see something quite curious. We see both a hit and a miss. So the hit refers to the synchronous behavior, the fact that Fastly is going to get that object out of the cache and return it to the user immediately. And that's why if we go further down to the deliver section, we see that the delivery of this object to the user was completed in 2 milliseconds, because we didn't need to wait for any origin fetch to make that happen. But going back up, you can see there's also a miss, which has this icon on it indicating it was done asynchronously, and then we've also processed the fetch to save that response into cache, which actually took 282 milliseconds. So you can see immediately like just how much of a performance improvement it is when we can use stale while revalidate to revalidate content in the cache, as opposed to making it a user wait for it. The other stale directive is stale if error. Now, if you use stale if error, then we will make the user wait, but that response from origin, if it never comes, will enable us to use the stale content in that scenario to avoid having to deliver an error to the end user, which would otherwise be our only choice. And if we have content that even if it's grossly out of date, then some content is usually better than delivering a really ugly error to a user. So use stale.
Yeah. To sum it up, stale content is good for you. You should serve stale while you revalidate in the background by using stale while revalidate. You should use stale content when your origin servers are down by using stale if error, because as Andrew said, you definitely don't want to be showing an error page to your users. And the way to make this work most effectively is to use a short stale while revalidate period and a long stale if error period. The long stale if error period could be very long, because if you're returning an error from the origin, there's really no harm in serving some older content instead.
Yeah, absolutely. And I guess that brings us to one of my favorite caching features, which is request collapsing. So the behavior that we exhibit when your content is fresh in cache is ideal, right? Like we have it in cache, we can serve that content at an incredible rate. We saw right at the beginning of the session how right now we're doing some 30 million requests a second. So we can dig content out of cache and serve it back to end users at a vast rate of requests per second. But if it's not in cache, then that's more of a problem, because we then have to fetch it from somewhere else. And it might take some time for the origin server to produce that content. And in that time, we might receive more requests for that same piece of content. So if we've already received a request for, say, your homepage, and it's not in cache, maybe it just expired, we've sent that request off to your origin server, and then immediately we receive another request from someone else for the same thing. Do we send that request to you as well? Or do we say, okay, hang on, we've already got a request in flight, we could wait and see whether the response to that request is public, and if it is, then we're able to use it to satisfy all of these users who are waiting for this kind of response. So that's what we do, and we call it request collapsing. So we have a couple of illustrations here which illustrate it quite well. So the problem is this: it's the overlapping request response. We have two requests from different users for the same resource, and both requests come in for either response is available from the server. And if we don't request collapse, then this is what happens. The server ends up having to generate both of those responses separately. With request collapsing, we have a waiting list, so we're able to say when that second request comes in, we'll tag it on to the first one and wait for that first response. And then if that first response is public, and that's a really critical point here, if it's cacheable and public, then we are then able to use it to satisfy both of those users. If it's not, then we can use it to satisfy the first user, the one that initially initiated it, and then everyone else will need to make their own request to origin. So let's demonstrate this, and for this I've actually gone over to Glitch, which we were using earlier on as a kind of back end for some of those fiddles. And I've made another glitch app. And this is a Node.js application that responds on the root path. It just sends back a static HTML page, and it takes 2 seconds to do it, so it's quite slow. It also counts how many requests it's received. So if I open the front of that glitch app, browse it, and I refresh it, it will take 2 seconds to load that response. And in the network panel down here, you can see, in fact, it wait slightly more than 2 seconds for the server response. And then if I go back to my server application, I can see here I received 1 request on the server for that resource. Now, I actually have a little bit of JavaScript on these pages that enables me to make 20 parallel requests for the same resource. So I'm going to click that, and then here in the network tab, you can see I've got 20 requests for the same thing. Each one came back. They all took just over 2 seconds. They all happened in parallel. And if I go check my server logs, I can see that I did in fact see 20 requests. So now let's do that through Fastly. So this is exactly the same origin server, but this time routed through a Fastly service. The Fastly service, by the way, is not caching anything that is coming through it. And I can prove that by loading this resource, which will take 2 seconds. There we go, 2.6 seconds. And then if I refresh it to try and load it again, it will again take 2 seconds because Fastly is not caching this resource. But let me go back to the server and clear this log. What happens if I click the Make Requests button? So again, 20 requests are being issued for this page, and they all take just over 2 seconds. But you can see from the X cache header, which is the column that I added when I was showing you the FT site earlier on, almost all of them are hits. Only one of them is a miss. But if I make those requests again, once again, they take 2 seconds, and one of them is a miss. Because Fastly is not storing this piece of content for any period of time. We're only storing it for just long enough to satisfy all those waiting requests. And if I go back to my server app, I press the Make Requests button twice, and I see exactly 2 requests. So this is extraordinarily valuable for any site that is receiving or potentially may soon receive a large influx of traffic to a small number of known URLs. Because without request collapsing, and especially if you have a backend that takes some time and does a lot of work to generate certain responses, you may well get overwhelmed by requests for content when it expires in the cache. So request collapsing.
So to sum that up, request collapsing is a way to combine multiple client requests together into a single backend request. If a request is not passed, it will qualify for queuing. And then any responses that are cacheable may be used to satisfy everyone on the queue who is waiting for a response. A hit for pass can be used to dequeue waiting requests in parallel. So it's really important that you add the private directive to any requests that any responses that shouldn't go to multiple clients. The reason for this is, yes, if you have an access to cache something by setting the correct cache control directive, we will not cache it. However, you'll see that these responses from the backend that were not cached for any other reason were used to satisfy multiple incoming requests. So it's really important that if you have content that is not going to be distributed to multiple users, that you use the private cache control directive.
Yeah, absolutely. And we've in fact had situations in the past where customers have inadvertently served private content to the wrong users because it's not marked as private. So if it is private content, mark it as private. Yeah,
and in fact it's really important that as anyone using a CDN that you understand the cache control directives and the ones that are required for different pieces of content, because you will run into problems where you perhaps serve the wrong content to the wrong people. And a great resource for this is actually on the Mozilla Developer Network, the MDN Web Docs, which has a great resource here for all the different cache directives.
Yeah, absolutely. And in fact, it's even though we tried to simplify it earlier on by saying there are really only three types of content. It's debatable, of course, and there's going to be a bunch of people who will argue with us on that. If you really want the sort of full fat understanding of what each cache control directive does, then this MDM page is a very good place to go to understand that. Especially, for example, the no cache directive, which is probably the most misunderstood cache directive because it is probably the most badly named cache directive. It doesn't actually mean don't cache. So yeah, take a look at this if you ever feel like you need a refresher on what cache control directives are available.
Okay, great. So why don't we move on to something that is a unique feature of Fastly that is especially powerful. Why don't you talk about shielding?
Okay. So up to this point, we have been dealing with a situation where an end user sends a request. It is handled by a Fastly POP, and if that Fastly POP doesn't have the object that the user's requested, then it will get it from your servers, your origin server. Now, it's tempting to think that Fastly POP is a singular thing, but it isn't. We have almost 100 of them. So if you don't do anything to try to reduce this, then you will get requests from each Fastly POP, assuming your traffic is kind of evenly distributed across the world and you're receiving traffic in every region where we have a data center, then you will actually get 98 requests for a piece of content before we've managed to cache it in everywhere in the world. Now with shielding, we can change that. And with shielding, what happens is every Fastly POP, when it needs a piece of content from origin, it doesn't send that request directly to your origin server. Instead, it sends it to another Fastly POP. And you can designate one specific Fastly POP. Now, this is usually the one that is closest to your origin server, but you can use various other criteria to decide what the most appropriate location is. And it will also depend to some extent on what kind of content you're serving and how much sort of volume of data you have. But in general, you receive requests to any POP that is not that designated POP, and if it doesn't have the object in cache at that location, that POP will forward the request to the designated shield POP. And that designated shield POP is then responsible for fetching that content from your origin server. And that means that if correctly configured and you start receiving traffic all over the world for a single URL, we will end up requesting that URL from your origin server just once. And that is, of course, assuming that you also it also qualifies for request collapsing, because request collapsing here operates at both levels. So if we're receiving lots of requests for that resource all over the world, we will collapse them all in each of those local locations. We will then collapse all of those parallel requests at the shield, and you will end up with one single request at your origin server to fulfill. So we can see this in action, actually. And earlier on, we showed you the FT website. I'm going to go back to the FT website and show you again. Go back into the Web Inspector and reload the page. And you might remember these requests here, these ones that said miss, hit. And that is an indication that those responses are coming through Fastly in a way that's been, it's been set up to be shielded. So there are two levels of caching effectively involved in this response. If I go back to the shield page, I could show you the bit of the page that actually tells you what those mean. So, if, for example, you see a miss hit value in that response header, it means that the object was found in cache at the edge, but it was the result of a prior miss at the shield. So essentially, we kind of stack up the Xcache values. So it was originally a miss earlier on, but then it was a hit later on in the stack. It can be quite confusing to think about these things when an earlier cache state gets saved into the Xcache header. But operating a shielding configuration will vastly improve your cache hit ratio and also vastly reduce your traffic to origin. So it is well worth setting up if you have a lot of traffic on your site. I have a little demo of this here. So again, using Fiddle, let me run this. So the only difference here, this is a completely standard configuration here. Again, I'm using that standard glitch app as my origin server. I'm just asking it for a plain old 200 OK response. And for my configuration here, I've just enabled shielding. Everything else is completely default. And so we see that we run a certain amount of the process at the first data center, which in Fiddle's case is Chicago. That's the first data center that any request from our Fiddle tool will hit. And then it shields to New York. And then we see the same process happening in New York. Then we see a request to the origin server. The origin server responds, we store it in New York, then we store it in Chicago, then we send it back to the end user that made the request. And if I run this Fiddle once again, this time we should see a hit, and we see a hit directly in Chicago because we have cached it in both places, but the second request is still going to the same edge location, so we see a hit directly and immediately at that edge location. Now, if I was to send this request to a different edge location, let's say London, pick a random location that we happen to be sitting in, then it wouldn't be in cache there. So that location would forward the request to New York, which would have the object because it's already been requested from New York via Chicago. So the origin wouldn't need to serve that object again, even though it's not present in cache in the local POP that my request would go to. The final thing I'll say about shielding is that the choice of shield location is quite important, and we've got a little tool here that we wrote and put on the Developer Hub to help you to decide where to shield your requests. Because it's not just a matter of which location is closest to your origin, it can also be just a matter of ping time, and it can also be a matter of how large is that location, because Fastly POPs vary in size. We also have some POPs that have private network interconnects with major cloud providers, and using those locations can provide you with a faster, more reliable, and potentially cheaper connection to origin. So let's type in, say, example.com, and what we're now doing is pinging example.com from every Fastly POP, so that we can give you an idea of which POPs would make good shield locations for example.com. So if you were the operator of example.com, then this is where you should shield. The obvious locations are Ashburn, Virginia, which is in fact one of Fastly's largest POPs. But there's various other places that would work as well, all of which are within 20 milliseconds of that origin location. And yeah, I could, for example, put in my own website, and I know my website is hosted in a DigitalOcean server in Amsterdam. So I'm expecting this to produce a different result to tell me that Amsterdam is the best place to shield this website. And sure enough, Amsterdam comes up green.
Great. So to sum that up, shielding is a way to focus all of your requests through a single POP, which will improve your cache hit ratio. For every period of your TTL, for example 1 hour, you may get up to 1 request per Fastly POP. With shielding, you would just get 1 request from the designated POP that you've chosen. The shield POP is then responsible for passing the content to other Fastly POPs, and it means that overall, requests for certain resources are not going to be hammering for your origin server. Okay, I think we have time to talk about one more feature that's going to improve reliability and speed of your site, and that is normalization. Okay, do you want to walk through that?
Yes, absolutely. So let's look at the code examples library on the Developer Hub. We have hundreds of code examples here. This is you get to this through solutions examples, and all kinds of interesting things you will find in here. But if you just search for normalization, I have to remember to spell that with this example here. I love how there is a normalized way of spelling normalization.
Ironic.
Very much. So this is a. I didn't want that example. A different one. I wanted.
There are lots of things that you can normalize, but I think the example that you're going to show is
yes,
query strings, correct?
Yes. So this is an example of normalizing request to improve cache efficiency, which I picked by accident about stripping training slashes, I think. But let's have a look at this example, which is the objective of this example is to try to improve our cache ratio by taking requests that are very similar to each other, they're semantically equivalent, but which normally would be considered different. Just make them the same, so that we have a better chance of hitting a result in cache. So this example, I can just run it on the page, but I'm going to open in a new window and it's to fiddle, so I can see and I can edit it and play with it myself. If I run it here, we can see what this code is doing to it. Now, this is the first example actually that we have shown today that actually involves writing code at all. So here we're writing VCL, Fastly's sort of proprietary DSL, domain-specific language. But you can also use our compute platform and you can achieve all the same things in Rust, JavaScript, or Go. So what is this doing? Well, we're receiving, first of all, quite a complex request from the client, the sort of request that you'd get from a browser, which will have headers like accept, charset, encoding, accepted language. You'll have a user agent header. This request also has a query string as well. And then we do end up presenting that same request to an origin server. But the request that we present to the origin server is quite different. It has fewer query parameters, it only has one, whereas my original request has two. It still has all of those accept headers, accept, charset, encoding, and language, but they're much shorter. They've been normalized to reduce the number of permutations and possibilities that those values could hold. So this means that we have a much better chance of finding this object in the cache. And in fact, if I make another request for this, I actually turned off caching there. Let me turn it on again. Okay, so I now have a hit. And if I add another query string parameter here, like Andrew equals 42, then look at that, magic. I got a hit again, even though I changed the URL. So normally this would not match that object in cache because it's a different URL and we would forward it to origin. This code that we've written has actually enabled us to use an existing cached object to answer this request. Now, it's up to you whether you want to do things like you could just alphabetize the query parameters, like, because normally if you were just to reverse two query parameters, even if they have the same values, that would still be a different URL. But that's a pretty low risk thing to do. If you just want to sort query parameters, we actually have a function to do that, querystring.sort, because it's a very easy and obvious way to increase cache efficiency with no loss of granularity or no reduction of data on the URL. In some cases, you know what query parameters are acceptable on a request, and so you could allow list the ones that are valid and remove all the others. That's effectively what this code is doing. Or you could say for certain URLs you don't actually allow query strings, and actually that is the case for the majority of URLs on the internet. Things like images, style sheets, scripts. Almost all sub-resources don't actually use query strings for anything. So for those kind of resources, just don't allow query strings, and you may well find that you're able to avoid a lot of requests going to origin. And the other thing we're doing here is we're normalizing some of the request headers. Now, that isn't going to improve cache efficiency by itself, but if your origin server is using the vary header to indicate that a response varies on some aspect of the request, like the accept encoding, which is very common for doing things like returning compressed responses to browsers that support compression and uncompressed responses to clients that don't, we would then store the compressed and uncompressed variants separately, and that is keyed on the value of the accept encoding header. So normalizing that will mean that we have to store fewer variants and we have a much higher chance of finding an answer in the cache.
Great. So you should definitely normalize your requests to maximize your cache hit ratio, whether that is removing or sanitizing your query strings, lowercasing your paths, normalizing headers like accept encoding. You should also consider redirecting to avoid serving the same content on multiple URLs. I think that links in with the code example that you accidentally showed earlier where you're removing trailing slashes.
So, I mean, the downside of this normalization process is that if you end up serving exactly the same content on multiple URLs, then that is going to potentially be a bad thing from a search engine optimization perspective. I'm an SEO expert, but I'm told that if you show a crawler exactly the same content on lots of URLs, then that can be a problem. So, whilst it's probably a good thing to normalize URLs to improve cache efficiency, you may also want to consider redirecting to a canonical version of the URL instead of serving the content. But redirect you can also construct at the edge, so it also will not add any load to your server.
So there have been some key ways that we would suggest you to improve reliability and performance of your website, whether it is e-commerce on Black Friday or whether you just have a blog that is really popular. But there are some other things you can do that we don't have the time to get into. Here are some examples of those. You could add a waiting room to your website to only let a certain amount of users in at a time. This is very popular with sites that drop very popular products at a certain time. If they took the load from every single user trying to purchase the product at once, they would certainly fall over. And we actually have a previous live stream talking about that. So if you head over to our channel and check out the Fastly Developers Live playlist, you'll be able to see when Journey and I talked about implementing a waiting room using our compute platform.
It was the first one, right?
It was the first one, I believe. There's also compression, which is something that seems like an obvious thing to do, but it's actually not enabled by default for a lot of web hosts. And I wonder if you could go into a bit of detail, Andrew, about shared dictionary compression.
Oh yeah,
briefly.
okay. So I found out this recently at the Performance Now conference in Amsterdam a few weeks ago, where Patrick Meenan did a presentation. I have a copy of it here. Yeah, so Patrick Meenan is a Chromium contributor and I think Googler, and I think he also was the main author of Web Page Test, which is this incredible tool that allows you to simulate, to do real device synthetic testing on the performance of your website. And he has been working a lot recently on something called compression dictionaries, and this would enable you to use a custom compression dictionary for various compression algorithms. The one that he spent most of the time talking about was Brotli. And this would mean that you would be able to refer to existing content in any response. So you wouldn't need to necessarily include the full content of the response when the client and the server already pre-agreed on a dictionary of common strings. And that's really cool. Like it's I haven't looked into it in detail, but he did mention in his talk he cited a bunch of edge networks and whether compression dictionaries worked with them. Unfortunately, it seems they do work with Fastly, so I'm very happy to hear that.
That's great news. That's great news. Yeah, I mean, it's really exciting to see the improvements that are being made to make these things even more efficient. I assume in the future that we're just going to send like 3 characters and represent an entire website.
Yes.
There's a couple more things that you can.
Well, I did. Sorry, I did find that out through Patrick's talk that some compression. In fact, actually, some of the improvements that Brotli has brought to compression come as a result of it having shipped like a compression dictionary as part of its standard library. So basically, the designers at Brotli figured out the strings that were most common, like on the web in general, and built them into the Brotli protocol. So, or not into the protocol, but like into the decompression implementation. So, I guess, I don't know whether that gets updated, but like as of whenever Brotli was released, there's a set of strings built into the browser that it knows about in advance. So you don't have to include those in any object that is Brotli compressed. I think that's really, really fascinating.
It's very fascinating, but knowing the internet, there's probably some questionable strings in there.
I don't know whether it has to be family friendly or not.
So there are two more things that I wanted to mention that you could consider to improve the performance and reliability of your site. Using Fastly specifically, one of these is domain consolidation. So I'm sure you're aware that many websites will have lots of content requested from many different domains. And this isn't always great for performance, as of course you need to do DNS lookups and TLS handshakes for all of these different domains. It also doesn't help your SEO. Search engines tend to prefer a website where all the content is loaded from a single origin. So you can help improve this with Fastly by setting up your service to serve all of the content from different backends under a single domain name. And Andrew actually wrote a really great blog post about this, which is titled "Taming Third Parties with a Single Origin Website." Walks you through how you can do this. In our example, we fronted Google Analytics, Sentry, FormKeep, and SwiftType. Any of your kind of third-party scripts or resources being loaded can actually be loaded through your Fastly service as well. We would definitely recommend that. And the final resource is, of course, having a web application firewall. Any kind of attacker attempting to exploit your site, perhaps using valid payloads to cause it to crash, or maybe just overwhelm it with massive amounts of requests, can be limited by using a web application firewall. And you can, of course, find out more about that on our website, because if you are using our CDN, you may be used to the protection that having another service in front of your website offers. But that isn't going to help if you're receiving malformed requests. If there is zero data that are being exploited to target your website. So with a web application firewall like Fastly, you can avoid that.
It's worth mentioning as well, having WAF enabled in your Fastly service will help to protect you against like a whole plethora of different potential attacks, including DDoS. But DDoS is actually something that just having an edge network in front of your site at all will effectively mitigate, simply because it has the capacity to take almost anything that is thrown at it. And also the fact that we're configured to deal with certain types of requests and just reject anything else. So, for example, things like memcache dereflection attacks or DNS attacks just simply don't work when your site is fronted by Fastly.
Well, Andrew, thank you so much for your time today. Thank you for sharing your vast knowledge of Fastly and CDNs. It was very insightful, and I think that in the future it's going to be a lot easier for retailers to protect themselves knowing these things.
Hope so.
Thank you for watching.
Thanks for having me.
Absolutely. Thanks to our viewers for joining us today. I hope you learned something. If you did, make sure to give the video a like and subscribe. I have to mention that. And we'll hopefully see you soon for another monthly developer live stream. Take care.